Okay, let's dive right into this explainer and journey to a seemingly quiet patch of stars known as Caldwell 16. If you look up on a clear night, the sky often looks like this static, peaceful painting, right? But as we're about to see, when you have the right tools and, honestly, enough patience to watch closely over decades, that peaceful painting gives way to a highly dynamic, almost chaotic cosmic neighborhood. We're going to unpack some fascinating research today that completely transforms how we view this specific stellar grouping. So here's our game plan for today. We'll start by meeting Caldwell 16, figure out exactly who belongs to the cluster, check out its vital stats and demographics, dive into just how dynamic this neighborhood really is, and finally, we'll unravel a giant exoplanet mystery.
Section 1. Meet Caldwell 16, a neighborhood in Lacerda.
Let's start by getting our bearings and establishing a spatial anchor in the vastness of the universe. We're looking at Caldwell 16, which you'll also see heavily referred to in astronomical literature as NGC 7243. It is located exactly 2,864 light-years away from us in the Lacerda constellation. Think about that for a second. 2,864 light-years means the light hitting our telescope lenses right this very moment left that neighborhood nearly 3 millennia ago. It's an incredibly distant, yet profoundly revealing pocket of our Milky Way.
Now, to really understand this neighborhood, we first need to define what an open cluster actually is. You can think of it kind of like a cosmic flock of birds. Basically, these are groups of stars that all formed at roughly the exact same time from the exact same giant molecular cloud. And because they shared this common origin, they're gravitationally bound to each other, loosely, but bound nonetheless, and they actually travel together through space as a single unified family against the background of all those more distant stars.
The history of how we've come to understand this cluster is essentially a story of relentlessly zooming in. William Herschel first spotted Caldwell 16 way back in 1788, and for a long, long time, it was pretty much just a faint smudge. Fast forward to 1937, an astronomer named Lengor managed to identify 39 specific stars that seemed to be members. But it wasn't until the modern photometric and astrometric surveys of the 2000s and 2010s that we really started unlocking the incredible details, expanding that membership list into the hundreds, and revealing some truly bizarre celestial mechanics hiding inside. Section 2. Who belongs to the cluster? Sorting the cosmic flock.
This actually brings us to one of the absolute most fundamental problems in astronomy. When you're looking at a two-dimensional patch of sky through a telescope, how do you actually separate the real cluster members from the thousands of random background field stars that just happen to be sitting in the exact same line of sight? It's literally like looking at a swarm of these in front of a distant forest. How on earth do you know which dots are the leaves on the trees and which dots are the bees? Well, the answer is patience. Immense, multi-generational patience. To solve this for Caldwell 16, researchers scanned photographic astrometric plates that had been taken over a massive 97-year period. By painstakingly tracking the exact position of these tiny dots of light over almost a full century, scientists were able to measure the exact proper motions of 2,165 individual stars in that specific region of the sky. And the data does a brilliant job of illustrating the sorting process. When you graph out the proper motions, the broad, flatter statistical curves represent the random, completely scattered movements of all those background field stars. But then you look closely and see these sharp, towering peaks right in the center. Boom, that is the cluster. By finding the stars that statistically fall into that super tight distribution, scientists can definitively say, okay, these stars are moving together, they definitely belong to Caldwell 16.
Section 3. Vital stats and demographics. The cluster's resume. Okay, so once we finally sorted out our cosmic flock from all that background noise, what did we actually learn about Caldwell 16? Well, its resume is pretty impressive. The demographics show a thriving, relatively youthful open cluster. Out of those thousands of stars they measured, researchers definitively identified 211 confirmed members down to a specific visual magnitude. We learned the cluster is roughly 250 million years old, which, in cosmic terms, means these stars are basically young adults. Altogether, the cluster has a combined mass of anywhere from 348 to 522 times the mass of our own sun, and sits at a true distance of about 698 parsecs away. So we've got this beautifully clear physical profile of the neighborhood. Section 4. A dynamic stellar neighborhood. The hidden action. Up until now, we've kind of been looking at Caldwell 16 as this quiet, still painting. But the reality, it is a highly volatile, ridiculously active neighborhood. When a dedicated team of researchers conducted a photoelectric search of the cluster, they weren't just looking at positions anymore. They were actually measuring the brightness of the stars over time, and they uncovered a sheer chaotic volume of activity. They discovered 37 brand new eclipsing binaries and 26 new pulsating variable stars. That is literally dozens of stars constantly flickering, dimming, and pulsing out there in the dark.
Just to really highlight the difference in the chaos we're talking about here, let's break down those terms. Eclipsing binaries are actually pairs of stars caught in this crazy orbital dance. From our specific line of sight here on Earth, they pass directly in front of one another, physically blocking each other's light, which causes the whole system to look like it's dimming on a super regular schedule. Pulsating variables, on the other hand, are single individual stars that are literally, physically swelling up and shrinking down in size. Their outer layers are expanding and contracting, totally changing their temperature and brightness. Just imagine 63 different stars in this one single cluster violently dancing and breathing like this.
Section 5. The Giant Exoplanet Mystery. And that brings us all the way zoomed in to an incredibly specific, totally baffling discovery surrounding just one single F-type star in the cluster, cataloged as J2255.6 plus 495611. While they were hunting for those variable stars, astronomers found a highly unusual signal coming from this one star, which, by the way, has a surface temperature of about 6,500 Kelvin. The data reveals this clear, distinct U-shaped transit signal that repeats exactly every 4.38 days like clockwork. Now, a U-shape like this, that is the textbook signature of an exoplanet. It means something round, dark, and separate is passing right in front of the parent star, blocking a portion of its light and then moving away.
But here's where the data gets incredibly weird, and exactly why astronomers are so captivated right now. The mystery is the massive 0.08 magnitude depth of that dip. That means whatever is passing in front of the star is blocking an unusually huge amount of light. To put that into perspective, even a massive gas giant like our Jupiter would typically only cause a fraction of this kind of dimming. The ratio of the planet's radius to the star's radius is roughly 0.2, which is absolutely enormous. So scientists are fiercely debating this right now. Is it an unusually bloated, oversized young hot Jupiter? Could it be a massive brown dwarf, like a failed star? Or is it just a celestial optical illusion, a grazing eclipsing binary star that just happens to look like a giant planet from our specific viewing angle? The data we have right now leaves all these thrilling possibilities squarely on the table, and we're going to need a high dispersion spectroscopy to solve it for sure.
Which brings us to our final thought for this explainer. We started with a faint smudge discovered by William Herschel over 200 years ago, and now we know it's this bustling city of over 200 stars, absolutely teeming with violently eclipsing binaries, breathing, pulsating stars, and potentially one of the most mysterious giant exoplanets we've ever stumbled across. If an open cluster located 2,864 light-years away can hide this much dynamic chaos and planetary intrigue, it truly makes you wonder, what else is hiding out there in the quiet parts of the sky, just waiting for us to look closely enough?